Hi students, this is Ms. Suchi here, and we are going to be covering Geometry, Chapter 6.1, Tangent Properties of Circles. Our objectives for this lesson are to be able to discover the properties of tangents of circles and learn applications of tangents. Now, the word tangent itself has many different meanings depending on what you're looking at. So this is going to be tangents related to circles. All right, now our first definition is to define a circle, which can be really tricky because circles are very common and something we've used a lot in our lives. But for geometry, we have to be really specific. So a circle contains a center point. If I start here with the center point, and then it looks like a curved line going around that center point, but remember, lines aren't curved. And so we're actually looking at point after point after point after point, all smashed together. And those points, representing this outer edge here, are actually all equidistant or the same distance away from the center. And that's because we have a specific radius when we're looking at circles. So we have a center point, and all points equidistant from the center. All right, investigation number 1. Review the terms related to circles by drawing a picture for each term and writing a definition. Now, some of these circles, or some of these terms might be familiar and some might be new. So let's look at each term here. So our first one is congruent circles. And we know the word congruent from our previous lessons. Congruent means the same size and the same shape. So if I have congruent circles, that means I'm going to have two circles that are the exact same size and shape. Now, because I freehanded these, they're clearly a little bit different in size. So I need to use some sort of marking to show that I meant for them to be the same. And what we're going to do is we're going to mark out how long the radius is. So a radius, remember, can go any direction from the center out to the edge of the circle. And because I want them to be congruent, we're going to use hash marks on that radius. So as long as my hash marks are the same, it's representing two equal radii. And if the radii are the same, then the circles are the same. All right, let's see here. What's going on? Let's close that. There we go. All right, the next one is radius. Now, radius is what we just marked up here. The radius is the measurement that tells us how big the circle is. So this right here would be the radius, the distance from the center of the circle out to a point that's on the circle. Now, I guess it says write a definition. I didn't actually do that here, so let me put that in. I'm going to use my typing thing so that it fits in here a little bit better. So congruent circles are two circles that have the same size radius and are the same size circles. All right, for radius, it is a segment containing the endpoint of the center of the circle and a point on the circle. All right, next word, concentric circles. So concentric circles are circles that share the same center. So something like an archery target or a bullseye or a dartboard would have concentric circles. So you'd start with a center point, we'd have a circle, And then we'd have another circle that matched that center point, but maybe was larger. Oh, my circle is terrible. Let me try that again. And then maybe another concentric circle where it's sharing that same center. So this also looks like the rings in water after you toss a stone into the water, how the rings go out from that same point where the stone hit the water. So in this one, concentric circles are circles that share the same center point. All right, the last one on this page is chord, and a chord is also a segment, but a chord does not have to touch the center point. It just has to have 2 points or its endpoints on the circle. So maybe I'll choose a point here on the circle and a point here on the circle, and when I connect them, I've made a chord. Now, that doesn't have to be where it's located. I could have it located somewhere else, like let's say I went this way, or I could have it go through the center of the circle itself as long as it's touching its endpoints on the edge of the circle. All right, now when we're looking at our chord, remember it has to touch the endpoints on the edge of the circle. But even if it goes through the center of the circle, we're not going to include that point as one of the points when we name the chord. So segment that contains endpoints, points on the edge, and I'm going to put edge in quotation because there's not really an edge on a circle, but that outer rim, I guess you could say, contains endpoints on the edge of the circle. Now, because we have segments for our radius and our chord, if we were to name those, we would use the 2 capital letters. So let's say I called this segment AB. And I would smash those 2 capital letters together and do the segment bar. Remember, segments can be reversed as well, so I could call this BA. For the chord, we're going to do the same thing. It's just a longer section, so I could say CD or DC for this case. Now, for the other one, if I had the center point listed, I wouldn't use that center point there. I would just say EG for that chord or GE. All right, next term is diameter, and diameter is actually twice the length of the radius. So the radius, remember, started from the center and went out to the edge, but a diameter actually goes both directions from that center out to the edge. So what we actually have here is a chord, but that chord must go through the center. So let's type that out. A diameter is a segment that is a chord that goes through the center of the circle. It is 2 times the size of the radius. And let me slide that up for us. There we go. Okay, now again, because it is a segment, if I were to name this again, it doesn't matter what letters I choose, so maybe I'll do M, N, center point O. I don't need to include that O, I just use the endpoints M and N. All right, the next one, tangent. So tangent is going to be our main topic for this lesson here today. So we need to know exactly what a tangent is. So here's our circle, and a tangent is going to be a segment or a line or a ray that just skims the surface of this circle. And so because of the way that the circle is curved, when we have a straight piece like this, it's either not going to hit at all, hit just once, or cross through it. And a tangent hits exactly at one point. And this point here is called the point of tangency. So let me type in that. A tangent is a line, segment, or ray that touches the circle only once. Okay, now for this one, I drew a line, and because I drew a line, when I go to name it, I'm gonna use at least, and you need 2 points for sure, but sometimes they have that point of tangency as well. So let's say I called this A, B, C. When I go to name this, I only need 2 of the points, and it does not have to be the point of tangency, but it could be the point of tangency that I use. So this one I could call it AC with the line segment above it. I could call it BC with the line segment above it. I could call it BA with the line segment above it. Any combination of those two of those letters with the line symbol above it would represent this whole tangent line. All right, central angle. So central, that's like our center, and angle is like the Pac-Man mouth angle. So what I'm going to do is I'm going to have an angle that comes from the center of the circle. So here's our center, and our angle is going to have its vertex right at the center. So this portion in here, that is our central angle. Angle where the vertex, or the corner, is at the center of the circle. Now because this is an angle, we would name it the same way that we do any other angle. So if this had P as the point here, I could call this angle P as long as there's no other angles around it. If we had 2 other points listed as well, we could name it angle QPR or angle RPQ. All right, next term, minor arc. So an arc is actually a portion of the circumference of a circle, and the circumference of a circle is the distance around the circle. So if I was going to do a minor arc, I want an arc that is less than halfway around the circle. So I'm going to use a different color here to emphasize it. And I want just the curved portion. And I'm going to have an endpoint on each of those. There's my center of my circle. Maybe I'll call this AB. And in order to name this, I would do it just like a segment. I'd smash the letters together. But now because this is a curved portion, I don't want a straight bar above it because that would represent a segment. I actually want like a rainbow curve above it, showing that this is the curve on a circle, or the arc of a circle. Now again, to be a minor arc, it just has to be less than halfway around. So an arc that is less than 180 degrees or less than halfway around the circle. Now for minor arcs, we just use 2 letters to name the arc. So they could throw in another point that's emphasized along the way there. We don't need to use that point because we're going the least amount of distance for a minor arc. We know we wouldn't want to go the other direction because that would be more than halfway around. All right, major arc is the opposite of minor arc. This one again is an arc, but it is more than halfway around the circle. So if I chose those same 2 points like I had before, I would not connect it up above here because that's halfway or less than halfway around. I want more than halfway around the circle. So this would be my major arc. And if I label this AB again, when I go to name this, if I just use the letters A and B, it's going to signal just this smaller portion. And I want this bolder red portion. So with a major arc, you do have to have a third letter. Now I do have to go in order, so I could name it A, C, B, or B, C, A. And then again, because this is an arc, we're going to do that curve like a rainbow right above it, showing that it's the curve around a circle. So a major arc is an arc that is greater than 180 degrees, less than 360. If it was 360, it would just be a full circle. Or an arc more than halfway around the circle. Let me adjust that so you can see it better. Okay, the next one is semicircle. So minor arc was less than 180. Major arc is greater than 180. A semicircle is exactly 180. It's halfway around the circle. So if I do this one, I need to have my endpoints of my arc straight across from each other. And if I were to connect those two endpoints together with a segment, or a chord in this case, it would go right through the center of the circle. Oops. So this one is an arc that is exactly 180 degrees. Oops, not 89. Or halfway around the circle. Okay, now with this one, as we're naming it, we also need 3 letters, because if I call this EF, oops, F, I wouldn't know if I was going around the top section or the bottom section. So I would want to have another letter here, maybe I'll call it H, and I could say EHF or FHE. And again, these are arcs, so they're going to be curved around to the top. Excellent. All right, now we actually get into the investigation relating to tangents. So all of that was just background knowledge, background information, so that we can talk about the different parts of the circles themselves. So in this investigation, we're looking at the tangent conjecture. It says point T is the point of tangency. So right here, this blue point or point T, that's where this line skims the surface of circle O. Notice they call it circle O because O is the center point. So the tangent conjecture says a tangent to a circle is blank to the radius drawn to the point of tangency. So if I look at the tangent compared to the radius, let me get a highlighter here. So here's our tangent, and here's our radius connected at that point of tangency. What angle measurement do you think is occurring between the radius and the tangent itself? Or how big do you think this angle right here is? And if you guessed 90 degrees, you are correct. And if it is 90 degrees, that means it is perpendicular. So anytime you have a radius connected to a tangent at the point of tangency, it creates a 90-degree corner or a right angle. So I'm going to draw in a 90-degree box to represent that 90-degree corner. All right, investigation number 3, tangent segments. This picture shows circle E, that's because E is at the center, with radius, let me highlight these radius parts here, EA, and radius EG. Now EA and EG, those would be the same length because they are both radii coming from the same circle. So technically, I could mark them as the same length. Points A and G are points of tangency, which means this line, or I guess this ray here, NA, is only hitting the circle once. And NG, this ray, is only hitting the circle once. The segments, let's see here, NA, which is this portion right here, and NG, this portion right here, are called tangent segments. Now, if I look at this picture, I can see that the radii are the same length. Both of these rays, these tangent rays, hit at one point on the circle, and then they meet right out here. And this shape looks pretty familiar. So, can anyone think of what shape we're noticing between A, E, G, and N? It looks pretty familiar from our quadrilateral unit. And if you thought that this looks like a kite, you are correct. And when we have a kite, we actually have two pairs of consecutive congruent sides. So not only are the radii the same length, but these tangent segments are the same length. So the tangent segments conjecture says tangent segments on a circle that meet at a common point, here's their common point that they meet, are congruent in length. Okay, now before we move on, because we have these segments, these radii connected to a tangent, we could also use the last property to show that these are meeting at 90-degree angles. All right, investigation number 3. I think that last one said number 3. I think this is numbered incorrectly. Yes, it is. All right, intercepted arcs and tangent segments. So what we have here is an intercepted arc. An intercepted arc is basically what the Pac-Man is eating. And so if I highlight the central angle, it is eating this intercepted arc right here. If you look at the size of the central angle and the intercepted arc, you can see that they're the exact same size. So down here it says, this picture shows circle O with central angle BOA that intercepts the minor arc AB because the arc is between the angle sides, or between the Pac-Man mouth. The measure of the central angle is blank to the measure of the arc. And because these two are the same size, we would say that they are congruent. So the central angle and the intercepted arc are congruent. Okay, now the next part of this question says, what is the reflex measure of the minor arc AB? The reflex measure is actually the other portion of the circle. So we're looking at this green portion, which is a major arc. So if we know that the minor arc is 40 degrees and a full circle is 360, we would just subtract those off to find the reflex measure, which would be 320 degrees. All right, in this problem it says mark all the known values on the figure to the right and then find the measure of angle T. So this corner right here is our unknown angle measurement that we're trying to find. But notice we have two radii. Those radii will be the same length because they're on the same circle. Then we have two tangent segments. They touch at the point of tangency and they meet each other outside of the circle. Those will also be congruent in length, but probably different than the radius. Because we have a tangent segment meeting a radius, we also have 90-degree corners here and here. And finally, they give us the information of this reflex angle measurement. So this measurement over here is 220. We can use that information to find the intercepted arc. So I'm going to start with a full circle of 360. Subtract off the 220. 0 minus 0 is 0, 6 minus 2 is 4, 3 minus 2 is 1. So that means my intercepted arc is 140 degrees. Now the arc that is intercepted is also the same size as the central angle. So this angle is also 140 degrees. Now if I take just the basics of this shape, we have a quadrilateral with two 90-degree corners, 140 degrees over here, and then the missing angle, which is our angle T. Now because this is a quadrilateral, quadrilaterals always equal 360 degrees. So we just need to subtract off what we know to find that missing angle T. All right, so 360 minus 140 minus 90 minus 90. Now, if you're like me, I'm not super great at doing the math in my head. I might want to have a calculator to compute this. But once you compute this, you should get a measurement of 40 degrees. So our measurement for angle T, this unknown measurement, is 40 degrees. Now another fast way to do that one is if you notice, because these are both 90s here, 90 and 90 together make 180, and 180 is half the size of the 360 total. So I just need to take 180 minus this central angle measurement to get our angle over here for angle T. So 180 minus 140 gets me 40. All right, here are summary questions that we will solve together to practice these conjectures related to tangents and circles. Thanks for watching.